Dear professors, welcome to our CZ4041 course project presentation. We are Group 3 and we will be presenting on the New York City taxi fare datasets on Kaggle. For today's presentation, we will be covering the problem statement, the data analysis, feature engineering, candidate algorithm, our selector model, which is the gradient boosting machine, and lastly, the conclusion. Firstly, let us talk about the problem statement. For the purpose of this competition, our team is tasked with one objective, which is to predict taxi fare in New York as accurately as possible. This prediction will be done using machine learning techniques that will be discussed further in the later slides. A brief overview of the New York City taxi system. In 1929, the Great Depression hits New York City, which causes a huge surge in taxi drivers. This surge was then regulated in 1973 with the taxi medallion system. Now, in the present, these medallions are priced exorbitantly high due to high demand and low supply. With our project, we hope to alleviate the taxi drivers' debt and bring other benefits as well. Firstly, being able to predict the fare will help the drivers to decide when and where they can find their passengers, thus increasing their revenue. In addition, taxi companies can use this information to maximize their earnings as well by determining when and where to deploy taxis. Lastly, passengers can use our project to determine how much money and time must be set aside for taxi trips as well. With an understanding of the project background, let us now move on to our machine learning itself. We start off with some data analysis that help us to understand the data better. From the slide, we did analysis on the fare distribution to allow us to have a better understanding on how the citizens of New York utilize taxi as transportation. With the fare distribution plotted out, we proceed to bin them accordingly with a width of 5 across $0 to $65. We then go a step further by plotting on the map with the different fare prices bins in different color. This proved important to us as the pink color plots highlighted an interesting perspective that is circled in red, that the rides to the airports are usually more expensive compared to other rides. With that in mind, our team noted this trend and will go into further details later. After having an understanding of the data, we began pre-processing the data in the datasets due to the anomalies present. Firstly, our team identified all NA values in the dataset and dropped the rows respectively. In addition, we also took note and dropped data points with unusual longitude and latitude present. Lastly, we move on to the dropping of fare amount that is less than $0. Moving on to feature engineering, we got a lot of inspiration from the New York City government's taxi website. It shows us that a lot of surcharges come from timing of the ride and where the ride goes to. Combining this information with our data analysis, we were able to come up with a few novel features, and they are distance, date time, clusters, and the airports. Let us talk about the distance feature. As the Earth is nearly spherical, the Haversine formula provides a good approximation of the distance between 2 points of the Earth's surface. It is a mathematical formula that creates these distances using latitudes and longitudes. With the Haversine distance feature in place, we found strong correlation between Haversine distance and fare amount. However, Haversine distance may be insufficient. Why do I say so? This is because Haversine only calculates a straight line distance to the destination, not taking into account road networks in the environment. As such, our team looked at additional features such as the actual driving distance as shown on the right. To calculate the actual driving distance, we chose OpenStreetMap REST API. To cover the discrepancy in the Haversine distance, we supplement actual driving distance too to make the feature perform more accurately. In addition, we also calculated the duration of the ride and therefore took into account. After incorporating the actual distance and the duration, we conducted an experiment to verify our finding. From the table, it is indeed an improvement with the addition of actual driving distance and duration. With this reduction of MSE, our team decided to utilize this feature in the model. Moving on to date time, our team had explored the pickup date and pickup time features as part of the feature engineering. For the analysis of the pickup dates, Our team plotted a histogram based on months plot. There seems to be a slight distribution trend across different months. Though these distributions are seemingly minor, our team still decided to incorporate this feature. Moving on, to observe if the pickup time features are beneficial, our team plotted a histogram based on hour and passenger counts. From the histogram, we observed that there is a peak between 1500 to 1800 hours. These peaks are most likely attributed due to the rush hour. However, though there is distribution we observe across the pickup dates and pickup time, our team decided to conduct experiments for the date time feature to verify if this feature is indeed meaningful. From the table, we can see a reasonable reduction in the MSE after incorporating date time features into the dataset. A 0.5 reduction of MSE in the Kaggle leaderboard proves that date time is indeed an important feature for the prediction model. With the data exploration revolving pickup and drop-off location in the early phase of data exploration, we also explored cluster features, mainly pickup cluster and drop-off cluster. Our team implemented k-means clustering algorithm on 500,000 coordinates to train a clustering model. In order to determine the optimum clustering model, our team plotted an elbow plot and selected 18 and 17 for the plotting of pickup and drop-off location clusters, respectively. Our team also conducted an experiment, and the reduction of MSE by incorporating cluster features are as shown. Though the reductions are slight, our team decided to include cluster features to ensure the prediction in the future will be as accurate as possible. Now, earlier I mentioned that we identified the airports contributes to higher fare. As such, we incorporated airport features into our model. This was done by collecting the coordinates of the airports around New York City location, mainly the JFK, Newark Liberty, and the LaGuardia Airport. Thereafter, we created a distance feature for each of them respectively to be incorporated into our model. And interesting results can be seen in the incorporation of airport features. For the Kaggle MSE, the control slightly outperformed the model with the airport feature by 0.01. Since the MSE gain in the training is more significant, we chose to add the airport features in our final model. To choose the right models for this dataset, we first had to identify that it is a supervised learning regression problem. Hence, it allowed us to shortlist 3 models to experiment with. They are mainly linear regression, random forest regression, and the gradient boosting machine. As a brief description, linear regression is simply to find the best fit line after training, and then predict using the said line. Random forest regression is to use multiple trees to predict the samples, and use the average of all prediction as the final prediction. Gradient boosting machine is an ensemble model that uses a tree-based learning algorithm for boosting. To ensure that we shortlisted the optimum algorithm, our team conducted vigorous experiments across the 3 models. The factors that were considered are the MSE training set, the MSE Kaggle leaderboard, execution time, and maximum records within the memory constraint. From the table, it can be seen that although linear regression is fast, its MSE value for both the training set and Kaggle performance came out to be the highest. An interesting insight from the table shows that the random forest is competitive. However, with a maximum records of 5 million data rows within a certain memory constraint, it will result in memory problems, hampering the team's flexibility when it comes to training of the model. Hence, our team concluded to adopt the gradient boosting machine as our chosen model due to the speed and accuracy it provides. That's a short overview. The gradient boosting machine is an ensemble framework that uses a tree-based learning algorithm, but instead of growing horizontally, it grows vertically. The criteria for node expansion is based on the largest loss amongst all leaf nodes. This expansion reduces more loss than a horizontal growth algorithm and provides better accuracy for the fair prediction. There are indeed many parameters our team had incorporated in the gradient boosting machine algorithm. However, our team would like to bring your attention to 3 hypertuned parameters that our team had adjusted and tested before coming to a final conclusion on which value to input. These parameters are learning rate, the column sample percentage per tree, the mean split gain. The table shows the experiment we have conducted for selecting a value for learning rate. True from the table, we can observe that the learning rate of 0.03 produces the lowest RSME. However, the time spent in execution far exceeds the team expectation for speed. Our team had collectively agreed that the emphasis would be the execution time instead of the MSE, as there is a slight differences between learning rate of 0.03 and 0.05. Thus, our team felt that 0.05 would be the appropriate value. For hyperparameter tuning in column sample percentage per tree, we had selected the value to be 0.8 after conducting the experiment. The value of 0.8 was intuitive due to the reduction of MSE across training set and the Kaggle leaderboard. Lastly, the mean split gain. For mean split gain, the MSE value in the training dataset did not differ much across the values we had chosen. However, when it was run against the Kaggle leaderboard, the value 0.5 came to be the lowest. Henceforth, we have selected our mean split gain to be of 0.5 in value. From feature engineering in the datasets to selection of model, and lastly, concluding an appropriate value for hyperparameters tuning with the selecting model. This leads us to the Kaggle performance. With gradient boosting machine and the features generated from our feature engineering, as discussed earlier, we were able to achieve a ranking of 85 out of 1,483 participants. This is top 10% in terms of leaderboard and is in line with the lecture that stated Zumbo learning is indeed powerful in machine learning. In conclusion, the team has learned a lot over the course of this project. We have faced many challenges, such as hardware constraint of the device we are running on. The project also taught us the importance of feature engineering and consideration we should take when it comes to model selection. In addition, the problems encountered with the datasets allow us to adapt and learn new models and skill sets through them. We hope you have enjoyed the presentation and thank you for your attention.